Okay. Gabrielle, if you can hear me, can you type something in the chat? I just want to make sure I can watch the chat without watching the stream to preserve what remains of my bandwidth. Awesome. All right. Okie doke. I think we're set up. It's just not quite what I was hoping for, but that's okay. All right, and you can all see OneNote, hopefully. Okay. All right, so we had a wonderful conversation last time about two-dimensional interference and the pretty patterns that it makes, the nodal and antinodal lines. We did some math. The key was it's all about delta R or delta X. That's our key. And in terms of whether our, by the time the waves reach a particular point, are they in phase with each other, making constructive interference? Are they out of phase with each other, making destructive interference? Are they kind of something in between, right? And we had some equations for that. Finding delta phi was our big one. And then also using that to calculate the amplitude. Okay, so we're going to do a few more kind of examples for this. So we talked about 2 dimensions. Same idea as 3 dimensions, really. You have your sources. You need to know, are they in or out of phase? Meaning, are they generating crests at the same time, or are they generating like a crest when the other makes a trough? And then if you want it at a particular location, you would find this distance r, and then do delta phi is 2 pi over lambda. Delta r or delta x, both fine. This is the same equation as the one we've been doing. I just switched x for r, and I switched k for 2 pi over lambda, right? Same as this one. Okay. Remember that this is not just 1r, and it's not the separation between the sources. The separation between the sources plays into it, but that's not all it is. So this is like, I'll call delta S. Okay. All of this seem hopefully familiar. There's some practice on the final homework to help you out. Okay. Can I get a thumbs up or a positive emoji of some sort? I have a lot of people in the team today. Did you think I was going to be doing review? Okay. Sounds good. Nice. That monkey just cracks me up. I don't know what the deal is with that monkey. Okie doke. So now we're going to talk about 1 dimension. 1 dimension is actually easier than 2 dimensions, which is why I do 2 dimensions first. So the same idea. Our delta phi is 2 pi over lambda delta x. What's delta phi not? Okay. Same idea, but Let's have a look. I have a little animation thing here. I have this one. This is the one I want. Screen, this one. All right. This is beautiful. Okay, important. Do not look at any of like the labels of like delta phi's and delta x's because this does it differently. Just don't look at it. They use delta phi where I use delta phi not. Just don't look at it. But this is an example of one-dimensional interference. I have a source that is making a wave. I have a source that is making a wave. They're making waves of the same amplitude, and they are located at different positions. And they are separated by some amount delta x. Okay. If they're at the same place at the same time, we'll start with that. Play. Right. So the bit on the right is showing you their interference pattern. So the key idea here is that anywhere along this line, along this axis, you're always getting the same type of interference. Are you standing right here, like right this location? I don't know if you can see where I'm pointing with the mouse. Right here. There we go. You will always see, you see big zero, double crest, double trough, double crest, double trough. You will see the extra loud wave. Okay. And then if you change the separation between these two sources, let me pick up the source. It doesn't want to let me pick up the source. I think I have to actually use my mouse. There we go. Okay. So they were totally overlapped. Okay. Then I move them some distance. And then I get less of the interference. This is still constructive because it is bigger than just one wave by itself. And I'm going to hear the same amplitude wherever I'm standing. Right? How far apart, this is a question for you, how far apart should I put them to get no sound? What are your thoughts? Oh, let me make this a little smaller so I can see my Twitch. Oh, that's why. All right. Sorry, I'm just pulling it up to make sure I can see what Twitch people are saying. So yes, all of those answers are correct. They should be off by half a cycle, so 1 pi essentially. 1 pi in terms of physical separation corresponds to a lambda over 2, which means a crest and a trough overlap. Okay, so I'm going to move this until it is precisely half wavelength away. If I can make it be precisely half wavelength. There we go. So they're still making crests at the same time and troughs at the same time, but now at a given physical location, the crest from one arrives at the same time as the trough from the other. And then it's destructive interference everywhere. Okay, makes sense? If I change my wavelength, then the same separation doesn't work anymore because it's not lambda over 2 anymore, right? There we go. Trying to make it like precise, and of course I'm screwing up. There we go. Screw it. I'll move this one. Okay. So the other factor that I can change, go to 0, you piece of crap. Fine, almost perfect. The other thing I can change is whether my two sources are both making crests at the same time and troughs at the same time. This is my delta phi naught. So if I make them off by half a cycle, now my blue is making a crest when my green is making a trough. But because of their separation, the crest and the trough, the crest and the crest will arrive at the same place at the same time. Wow, everything is lagging super hard. It's great. If I had them at the same place, they would just be canceling each other out. Right? Doesn't want to let me do it. Okay. If I put them half wavelength apart, now I get constructive. If I put them a full wavelength apart, now I'm back to destructive, right? So there's these two factors. There's the separation, and then there's the phase difference in terms of when they're making it. If they're just sort of kind of offset, right? They're not completely opposite. I can still find a separation where I get maximum constructive and where I get perfect destructive, but it's not going to be precisely lambda over 2. I could figure it out knowing my lambda and my delta phi naught. Okay. All this making sense. The one thing I want to emphasize here is that your delta x, if I have a speaker here and a speaker here, and I'm interested in the one dimension, and I have a person listening right here, which I'm going to illustrate with a giant ear. That's what ears look like. It's got some hair. Okay. Oh, you can't see that. Oh, you can't see my beautiful ear. Fixing. There we go. Okay. Sorry, I'm lagging really hard today. So here's a speaker. We can illustrate speakers as like a little box. And then here's another speaker, a little box, a little. And they're both playing along the same axis. And then I put a large, that's a human ear, obviously. Ears look like. Oh, I don't know, that's an ear. Okay, so you have x1 is the distance from this speaker to this one. This is the distance from this speaker to that one. And your delta x is still those two paths subtracted. Still the path length difference. But now that happens to equal the separation between them, delta x. I just want to make sure you don't think, oh, delta x is the separation between them. Nope. Okay. How's this going? Good, bad? I don't want to spend too much time on it because we have more fun things to talk about. Okay. So we have done 2 speakers. Give me like an emote in the chat or something so that I know this is working. So we had 2 speakers that were just playing in all directions. Okay. Right. All directions. Right. We had 2 speakers that were playing in the same direction. Right. What about if we have 2 waves coming in opposite directions? Opposite directions. So I have a little simulator for you, hopefully. That's a good one. Okay. Good. Okay, let me pull up my thing. Oh, okay, wait, I have to play this little corgi and see what it does. Oh, it's just windy. Oh, so nice. Okay. All right, so this in slow motion for you. I'm going to turn down this wave really low. So we have here I'm sorry, it won't let me turn it all the way off. Oh, here we go, high blue wave. Okay. I have a wave traveling fairly slowly. Let me turn it back into real time. No, I don't want to do that. Can I just turn off this wave? No. How did I make this faster? There we go. Okay, slow motion. So I have an orange wave traveling to the left. I can also do this as a why is this thing so crappy? Go. There we go. A blue wave traveling to the right. If I have both of those things, right, I have a blue wave traveling to the right. I have an orange wave traveling to the left very slowly. Okay. I have these points. So we look at this point right here. It's not my tab. Don't judge my tab. Half of these are simulations. Okay. So right here, we have a moment where two troughs arrive, one from the blue, one from the orange. Then we have two zeros. And then we have two crests, one from the blue, one from the orange. And then zero, and then, right? So if I were to stand at this physical location, I would experience the double crest, double trough, double crest, double trough, right? I would experience maximum constructive interference. So that point would be an anti-node, right? Whereas if I look at a point, say right here, when the crest arrives from orange, it's always a trough from blue. When a trough arrives from orange, it's always a crest from blue. So at this point, they're always going to cancel out. You can get it with sound. You can also get it with light or waves on a string or lots of other things. So in terms of sound, if you stood right here, you would hear nothing. If you stood right here, you would hear a very loud sound. Right, let me put it back into real time. Okay. So in terms of, if we picture this as waves on a string, right? There are locations where the individual piece of the string is moving a lot, and there are locations where the individual piece of the string is not moving. What the string is actually doing is shown by the green. Okay. This all making sense? Is this wave going to the left or to the right? Logan's poured some salt out in the Twitch chat. I don't know what the deal is there. And he says neither. Yeah, it's not going left. It's not going right. It's just standing there. So we call this bump-a-bump a standing wave. Which you can't see because I have it in the wrong share. There we go. Standing wave. Yeah. Standing, it's not traveling, it's just standing there. So it has nodes that are locations with perfect destructive interference. Destructive interference. I'm being so lazy here. Perf distant. You know what that means. Physics uses the first word that comes to mind, yes. Usually. Whoever thinks of it gets to name it. Them's the rules. Maximum constructive interference. Okay. And you will get a pattern, which we often draw by doing like something like this. Oh, pretend that goes over like that. Whoops. Right. So we have, we're slightly off. Right. So this is representing that whoom, 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 whoom. This is supposed to be constructive interference. So what we're doing is we're showing sort of both the top and the bottom, right? And then the places that don't move at all are just the places where it seems to intersect. Okay, so this and this would be nodes. And then right here and right here would be antinodes. Okay. Away. Right. So if I asked you, okay, here's a wave pattern. Can you tell me anything about the distance between two nodes? And we can, you know what, I'm going to be lazy here. Share my desktop, and then I can just switch windows and it doesn't suck. Right, looking at our thing, can you tell me anything about the separation between this point right here and this point right here? I can put it in slow motion to help you. Skylar has a thought. What do the rest of you think? Yep, have wavelength. You're correct. Lambda over 2, right? What about between antinodes? Also lambda over 2. What about between a node and an antinode? If you guess lambda over 4, you're correct. Good job. Excellent. Okay. We're going to skip the math on this. But why this is, it's fine and it makes sense. What we are interested in is sort of, you can think of this as kind of the extreme case of two-dimensional interference. If you have two speakers that are playing in all directions, you're going to get standing waves in this range, right? You have locations where there's an antinode halfway in between, you'll get an antinode, you'll get nodes. So you'll get a standing wave pattern right there, and then you'll get that lovely like antinodal lines, nodal lines, nodal lines, antinodal lines pattern. Okay, so that's one place you might see this. Another place you might see this is reflections, because this is how you get two identical waves, really. The easiest way to get them is a wave travels and then bounces off. So I have another animation for you. I should post a link to like all these fun animations. The internet is freaking magical sometimes. Okay. Start. Manual. Yes, this one is familiar. So we talked about if I wiggle this, right, it just goes out the window. But what if I attach the other end? Did you do this with them in lab? Yeah? So reflections from a fixed end, what happens? Use oscillation, okay. Tell me what's happening here when it reaches the end. The sound wave reflections act the same as light reflections. Yes. In terms of this, yes. There's some subtleties in terms of what's physically happening being different, but they do this. They flip upside down. Yeah. So what's happening here? When a wave reaches a fixed end, it will reflect, but, okay, bounce, but, okay, maybe if I show you a different situation, you can see what I'm getting at. But if I have a loose end, yes, opposite, upside down. If I have a loose end and I go, it does not flip upside down. Stays right side up. It flips when it reaches the fixed end, the wrench, but at the loose end, it just does its thing. And you did notice there's like, it's extra big right there, because what's happening at that loose end is this is actually that idea of interference. You have the one that's going to the right and the one that's being reflected at the same point. So you get like a double crest right there, and you get double trough while it's being reflected. Whereas if the end is fixed, your crest is being reflected as a trough, and so this point, this green ball, never moves. Okay. So in this case, I have a node at both ends. In the loose end, I have a antinode at that end. Okay. What happens if I, instead of doing that, I make it oscillate? Okay. Play. See kind of the weird pattern stuff happening here? Let's see what happens if I make it a fixed end. That's what I was really looking at. Right. What am I getting here? I get a standing wave, hooray! So I only had one source, this little wheel over here, but because it is reflecting off of a fixed end. Wow, Twitch is lagging really hard. I'm really sorry, Logan. Right. So this is not quite perfect. I couldn't figure out how to get it quite perfect, but it's as close as I could get it with the resolution of this thing. Okay. So I have a node right here. I have an antinode right here. I have an antinode right here. Okay. What happens if I change my frequency? Let me just roll it down to something super random. Let me stop and restart. So I've changed my frequency, which is sort of the rate at which this wheel is spinning. You can kind of see, like, oh, maybe there's a standing wave. Maybe, no, never mind. Died out. Right. So the nodes move, yeah, but I don't really have a node. I can't identify any point on here where I will get a node all the time, right? So the lesson here is that if I have if you have, for reflected waves, you have some distance between the ends, right? This is dictated by the physical situation. So only some frequencies will set up a standing wave in that space. So 37 did not. Oop, where's my mouse? Uh-oh. There it is. Lost my mouse. 50 kind of got pretty close. Because the reflection is not equal to the original. It's not so much that the reflection is not equal to the original, but we're going to talk about why. The reflection is equal, but let's see, how about another kind of about 60-something, 80-something. I'm going to make the amplitude a little bigger so you can see what's going on. So I made a higher frequency. Oh, kind of a standing wave? Kind of a standing wave, maybe? So, okay, oh no. Oh, no. RIP standing wave. Dead. Oh, is it there? Is it? Nope. Oh no. Right, so you kind of get a standing wave pattern and then it just dies. So let's try a different frequency. How about 1 hertz? Oh ho! This is not quite perfect. Let's see if 101 gives it to me. No. 199. Increase the damping and decrease it. Oh, does it sometimes have problems? Pretty good. It's not quite perfect, but it's pretty good. Sorry for like the weird lag here. Let's make this a little smaller. It's too much. So some frequencies work, some frequencies don't. What is the distinction here? So the key is going to be, if I look at my fixed end, where the vise is that a node or an antinode? Right. That point is not moving. It's a node, right? Yeah. So I have a node at one end. What's happening at this end with the wheel? Antinode. It's actually kind of close to a node. It's not quite, but it's close enough, right? If you watch this little green blob, it's moving, but it's only moving a tiny bit. compared to, say, this red blob right here, that is moving a heck of a lot, right? Yeah, it's moving, just only moving a little bit. So let me see. Did I have one that was time? No, that's not what I want. So basically, the ends give you rules. It's like a fixed end, means it has to be a node. A free end has to be an antinode. So for example, if I swap back to here, I'm going to restart. I'm going to make this a loose end. So for this same frequency, do I get a standing wave? Kind of not. It sort of tries to and then dies. But, and you can tell because if you watch a particular point, it's like, oh, right now it's an antinode, and then like 2 seconds later, it's like going to be a node, and you're like, wait, right? Like, what's going on? I can pick a different frequency. Getting there, not quite. Let me restart because it's got the other wave still waddling around in there. That's pretty close. No, maybe not. Whoops. Ah. Whoop. Too far. Make sure I'm doing this right. Let's pick. Should be pretty close. Make it a little bit bigger so you can kind of see a little bit better. Not quite. It's really frustrating. It doesn't quite give me what I want. 124. I need one that has a more precise control over their frequency. Dang it. Not working very well. Let's look at this one. There we go. Slow motion. So if both the ends have to be an antinode, you end up with a standing wave pattern. That looks like that. Okay. Is this sort of making sense? So if we think about a physical structure, of length L with a node at both ends. right? So I know here is a node, and I know here is a node. Okay, and I make a wave in here. Make a wave. It will have some frequency f that is determined by the source. And it will travel with some speed v, which is determined by my physical structure. So this might be light, it might be sound, it might be the speed of a wave on a string, it could be any of these. If I know f and I know v, that means there's a particular lambda. And I know if this is a node and this is a node, then the distance between these two has to be what in relation to lambda? Right, we talked about the separation between nodes. If, this is a big if, L equals something. So Logan has a thought over on Twitch. Does the length have to be divisible by the speed of the wave? No, because you have meters and meters per second, but it does have to be divisible by something else that's also in meters. Okay. I have a node at both ends. I know the distance between nodes. Wavelength. L equals n lambda. You're all very close. Lambda over 2. Right? I will get a standing wave. You can also think of it the other way. For a given lambda, if L is equal to lambda over 2, I will get a standing wave. For a given length, if the wavelength is twice the length, I will get a standing wave. But if it's not, I won't. I will get that weird pattern that doesn't really form a standing wave. Okay. And what does that look like? That looks like I have a node here, I have a node here. I will have one antinode in the middle because them's the rules. So my pattern will look like this. Okay. This is lambda equals 2L, L equals lambda over 2. Is this the only pattern that'll work? The only way to get a node at each end? Andre, I think, has a suggestion with an equation, but no, okay. I can also make a pattern that has 3 nodes and 2 antinodes. So it has a node at each end and a node in the middle. Right. In this case, L equals, is it still lambda over 2? Andre's like, I want the equation. Double. So it's lambda over 2 plus lambda over 2. So that means the length is just lambda. Andre, you're getting closer, but you're still not there, I don't think. Okay, my next one, I have same length. This is going to be a total of 4 nodes and 3 antinodes. So 1, 2, 3, 1, 2, 3. L equals lambda equals. This one's a little tougher. I find it easier to think about lambda one wavelength is going to be here plus here. So that is 2/3 of the length of my thing. So this becomes 3 lambda over 2. Let me keep going. I'm going to do a couple more so you can see pattern. I have 5 nodes, 4 antinodes. 1, 2, 3, 4, 5. Pretend these look decent. Okay. So one wavelength is half of it. So lambda equals L over 2. L equals 2 lambda. I can do 6 nodes, 5 antinodes. Tell me when you see the pattern. Andre's pretty close, I think. Yes, I think Andres might have been right. M lambda over 2, yeah. You are both correct. So we end up with, okay, 1, 2, 3, 4, 5, 6. Did I draw too many? I think I drew too many. 3, 4, 5, there we go. Nah. 6 nodes. 1, 2, 3, 4, 5. 2, 3, 4, 6. There we go. Sorry, Andre, I was looking at it wrong. Really, my note is right here. So this one is a little bit harder. We can do it the other way. Okay, there is 1, 2 and a half. So 5 halves lambda. Lambda is 2L over 5, so it's 2/5 of the length. And then by now you will possibly found the pattern. This would be the same as 4 lambda over 2. And this would be 2L over 4. This would be 3 over 2, 2 over 3. This would be 2 lambda over 2, 2L over 2. This is, I put these backwards, that's really annoying. 1 lambda over 2, and lambda is 2L over 1. So our pattern is lambda is 2L over M, L is M lambda over 2. This is the form you see more often, but you can easily just move it into this one. It's totally fine. This one I think makes more sense. Oh, the length has to be some number of half wavelengths. Okay. M is sometimes what is called the order or the harmonic. It also stands for the number of what? This number is the same as this number. Antinodes. Yeah, antinodes, good. So if you see something on a test that is like, and it says, okay, what harmonic is this? What harmonic is that? Two. Antinodes. It's tricky. Okay. So, harmonic. You may see the application of this. Why do we care about standing waves? What's a really great application? Instruments? Yeah, music. So musical instruments almost entirely work along the along this physical basis. Wave pools also, yeah. You also have, if anybody has anti-glare lenses, that's a place you use it. It has a lot of applications. If you have cold spots in a microwave, that's standing waves. That's more of a problem than an application, but yeah. So there's lots of, so it was for harmonica, like not specifically harmonicas, but yes. So each of these has an associated frequency with it, right? So for a given V, so this would be light, sound, the speed of a wave on a string, right? There will be some F that is V over lambda. So this one would be, you can also put it in terms of lambda is 2L. So this would be V over 2L. This one would be 2V over 2L. This one would be 3V over 2L. This one would be 4V over 2L, etc. The frequency is mV over 2L. M equals 1 is the fundamental frequency of that wave. This is what you hear, like if any of you musicians, if you play an instrument, you will hear like, oh, A is traditionally 440 hertz. That is the fundamental frequency. You will get all the other harmonics, and how much you get of which harmonic is kind of what gives an instrument its sound. But this is the one that determines the sound that it makes. So let's talk about this. I have some props. Let's see if I have. I'm just gonna look for a tuner here. Oof. Boring. While I try to find a good violin tuner app. I have a physical, oh, I don't want this. I want one that I can use online. I have one on my phone, but I want to be able to like show you. Online violin tuner. I want one that actually uses my microphone. Online with mic. This one has a lot of crap on it. Not working. Whoop. So my physical tuner is broken. I have one that's broken and I have one that's in my office. Oh, ho. Allow. Okay, is this gonna work? Oh. My display, my prop for the day, right, is an extremely out of tune violin. This is actually a violin. It's an electric violin. That's why it looks so weird. I am clearly a very organized and prepared instructor. Oh God, it's terrible. Get it at least reasonably close. Oh, that's great. Snapped my E string. That's because that was the wrong one that I was adjusting. Okay, can this hear it? Nope. I should find the needle. Okay, take off my mute. That's definitely not 440. Work. Microphone access. See if this works. If not, I'm just going to give up. Download Flash Player. Have Flash Player. Tuner. Wow. There we go. I didn't think about doing this before. So this plays a note. Why does it play that particular note? Because it has a particular length, L, from this point up here, right, where the string touches, and then this, the bridge right here, right? This is what's called the oscillating length of our string. Okay. You will note that the source of it is not at either end, it's right here. By plucking it or by playing it, I am generating, oh gosh, sorry, Logan. I don't know what the deal is with OBS today, it's just not working well. So I am, by plucking, I am making it oscillate. I'm creating a pulse. And that pulse is, I don't want to say every frequency, but lots of frequencies, right? But only some of them are the correct frequency. So for a given length, right, only certain frequencies will create that standing wave pattern, right? So it depends on the lengths from here to here. It also depends on, okay, this is just not working. Forget it, it'll just be super out of tune. So we have the length of the string. We have V, which is the square root of T over mu, right? What are T and mu? We talked about this before. I don't know if you remember. was actually super quiet. I was afraid to play it in my apartment, but it's so quiet that I can probably get away with it. I don't have an amp anyway. Yep, tension and linear mass density. So, tension. Tension is what I control with these pegs at the top. By twisting them, it wraps up the string and then makes it tighter. So, if I turn the peg, I turn the peg, well, I was hoping this would be big, and make it tighter, what happens? More tension. More tension means what happens to V? V increases. So if V increases and my L stays the same, what happens to F? Higher note. Good. So this is my A. If I turn the peg, which peg is it? This one. Higher. Right? If I have several different strings. Ta-da. Can you see that they are slightly different thicknesses? Right? So what that means is the same string, it's got the same, well, okay. If I have each of these strings has the same length, I could turn them to the same tension, but they wouldn't sound the same because they have different linear mass density. So this is mass divided by length. So the thicker and heavier it is, the thicker string will have a lower V, which means it will have a lower F for the same tension. Right? So another thing I can do, I can put a finger down. What happens if I put a finger down? Right, those of you who play guitar, it's about which fret you're on. Put a finger down. Shorter L. So if I put a finger down, that means I have a shorter L, but I have the same V. So my fundamental, which is V over 2L, is going to be higher or lower? If I put a finger down, will I get higher or lower frequency? Higher. See if that's right. I'm not a very good violinist. It's also super out of tune, but I put a finger down. Right. Oh, God, it's so out of tune. Okay. Making sense? All good? Okay. I have a little bit more to talk about. So I'm not going to really talk about a problem at this point, but I want, if you understand how this works, standing waves are super easy and cool and like instantly get a ton of questions right on your final exam. P. I don't know what that is. P. Okay. So not all instruments have strings. I know I'm going to go a little bit over. I'm really sorry. What's an instrument that doesn't have strings? Keyboard. Digital keyboard is kind of like, okay, well, it makes music electrically. Physical, like piano, those are strings. Do they make the air wiggle? Yes. Excellent. Harmonica, yeah, harmonica. Harmonica is a little different, I think. Yeah, not 100% sure how a harmonica works. I have one around here somewhere. So you have like wind instruments. So the air wiggles, right? So our V is the speed of sound. So we cannot really adjust the speed by adjusting the tension the way we do for a violin. You're kind of stuck with it. So usually what you do is you have more control over the length. But the idea still works the same. I have a demo around here somewhere. This one will do show wave as sound, real time. Right. So the green is the individual air particles that are moving. The blue and the orange are those like, where's the crest, where's the trough? But you have sort of, do I have a node or an antinode at the ends? So for this, the node or the antinode at the end has to do with node versus antinode, has to do with whether it is a closed end or an open end of a pipe. So the simplest example of this is the open pipe, like like an organ pipe. If you have a toilet paper tube, perfect, right? If it is closed at both ends, you get the same patterns, as for a string. If you have something that is open at both ends, closed at both, this is open at both, still, now it's going to look a little different. It's going to look like this, because now I have an antinode right here and an antinode right here. But I still have one node. This is still lambda over 2, right, from a crest to a trough. So the math is the same, but M becomes the number of nodes. Otherwise, it's all the same. Same math, same pattern. Okay. If it is open at one end and closed at the other, things get weird. Because I have to, fell off my chair. I have to have a node right here, and I have to have an antinode right here. So my patterns are going to look a little different. My fundamental is only going to be lambda over 4 instead of lambda over 2. And then if I do lambda over 2, this would have a node at this end, but it has to be an antinode. So this is not allowed. The next one would be, I have one node and an antinode. So this would be, I'm trying to make sure I have the math right. Okay, that is 2 lambda over 4. This is 3 lambda over 4. It's 3/4. That's allowed. But if I do lambda, 4 lambda over 4. This is not allowed. It would give me a note at this end, but it can't be. So for an open closed tube, it is our L equals m lambda over 4, or lambda equals 4L over m, but only, wow, Logan is really far behind. They're vibrating reeds. They are vibrating reeds, but I don't remember how they select the frequency, because a reed makes all these different frequencies, and then the length of your tube determines which sound you make. This makes only odd M's. So yeah, I'll have to get my harmonica out and see. So there is something called overblowing, which is how much air you use. That usually will select a different harmonic. Select m equals 2 rather than m equals 1. So I have an example of a wind instrument. This is a recorder. Super fun. Horrible sounding. This I definitely don't know how to play. Violin, at least I played when I was a kid, but recorder is no. There is no recorder skills whatsoever. But it is a tube. The air inside the tube is going to oscillate back and forth. The speed of the wave is the speed of sound in air at this particular temperature, which is really hot. It is open on this end, usually for a recorder. Oh God, I can't even play hot cross buns. That's how sad it is. At this end, it is closed because your mouth is there. The source is this right here. It's not like a reed. It's just like a gap, right? That makes all the frequencies. And then the length of this tube determines which one is selected as the standing wave, and that's the pitch you hear, right? So I'm going to hold down some of the holes, right? It has holes all along length. So it goes. Isn't that a wonderful noise? It's fantastic. I have a tin whistle around here somewhere, it's even worse. So I have a closed end, I have an open tube, and I have these holes. The holes are essentially forcing an antinode, right? This one's closed, this one's closed, this one's closed. If this one is open, this forces an antinode right there. It pinged my mic. Oh no, I'm sorry. My tin whistle might be a lower key. I should grab that one. So this forces essentially this wave pattern. This is our L from the mouthpiece to the hole. Okay. So if I hold down more fingers, what will happen to the sound? What happens if you skip a hole? That's a really good question. I think it basically just ignores everything below it. Has a small effect, actually. But in that case, if you're skipping a hole, you're forcing an antinode there and an antinode there. So you're going to get, I think, some weird. Yeah, I think it was just that one that I picked because it happened to be like the halfway. If I skip some random other hole, mostly the same. It affects the harmonics, I think, more than anything else. All right, tell me what happens if I hold down more fingers while I find my tin whistle. For someone who is not a musician, I have a truly hilarious number of musical instruments. Okay, so Annie has a thought, lower frequency there for a lower note. Okay, so more fingers generally means a longer tube, right? Because now these holes are all blocked. Now there's a hole right here. Longer L, same V because it's still the speed of sound. I get F equals, this is MV over 4L. Right. So if L goes up, F should go down. So let's say I played this one, I think. Let's add more fingers. Yeah, lower note, good job. Okay. I'm going to talk about two more things really quickly. One is, let's go way back here. Ooh, beautiful. If I tune my violin correctly, then I will get, my fundamental frequency will be 440 hertz. What will be my second harmonic? Other way. Good try though. So our lambda has gotten shorter, which means our F has gotten bigger. So this will be 880. What about this one? What about the third harmonic? Yes. They go up in multiples. So our F, the mth harmonic, we call F sub m, is equal to m times the fundamental. So if I have a, if I tell you there are three frequencies, or I don't know, if I tell you 440 versus 442, so hang on. So the third string below has the standing wave pattern at 450 hertz. What's the fundamental? So if I show you a pattern like this, and this is, if I put in a frequency, I will get this particular standing wave pattern at this particular frequency. What's the fundamental? So while you're thinking 440 versus 442, I think it's just about, like, historically there wasn't a set A. So different composers had different A's that they preferred. So sometimes you will get people tuning it down to match more of a historical value, but we don't know what all the historical values are. I have no strong opinions. I'm half tone deaf anyway. 150, you are correct. Noel, how did you get that? Divided by 3, yep. How did you know that it was 3? Oh. Counted the antinodes, good job. So this one, because it is closed at both ends, you are going to count the antinodes. It's a good question. If it's open at both ends, you count the nodes. And if it is closed open, you just got to work it out because it sucks. So like you count each node and antinode, but you divide by 4. So 1, 2, 3. Actually, no, 1, 2, 3, 4. You minus 1 and then divide by 3. It sucks. You just figure it out. Draw it. Okay. So I hate that I haven't had time to really talk about any like problems. I'm really sorry, but I feel like if you understand the fundamentals, the problems will make some sense. So what I might do is do some problems at some point during the reading days or something, or just pass some, or help you with the homework, things like that. So Logan and I actually talked about beats the other day. We did find my chin muscle. Is this a lower sound? That's better. Yeah. We talked about beats, which has something to do with tuning an instrument. Yes, I will do a meeting during one of the reading days. So there are questions on your final homework about beat frequency. Beat frequency just means beats. If you have 2 slightly mismatched waves, they will go wow, wow, wow at a rate that is equal to the difference between them. That's kind of it. That's sort of the extent that you really need to know. But you use it for like tuning. Why is my A always broken? That one it broke. Getting closer. You can't quite hear it. I think it's 2 out of 10. But you will hear. Let me pull this up really quickly. Oh, there it is. No, don't move. Beat frequency. Okay. It's a cool video. Which I will post a link to because the noise is really annoying. And you can hear what I mean by beat frequency. So you will hear like a wow, 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 wow. And the more, it has to do with the amplitude envelope. I just want you to be able to do the homework problems on it. So beat frequency is the difference between the two, and it's the frequency of the wow, wow, wow noise that you hear. If you want to look at it in your book, it is in your book. All right, I will stop there. I know I've gone way over time. Thank you all so much. I will do some review stuff in the reading days and definitely in the day of and the day before the exam. I'll post announcements for things as they come. Yeah. Any last questions about anything before I let you all go? Yeah, I like it. I think it's a cool video. All right. Send me an email if you have questions about stuff. Thank you all so much. I'm really sorry that this is what your semester turned into, but I've had a good time. I feel bad that I'm always just slightly over, but like I feel like 20 minutes is not bad. Ooh, Logan has a recommended video for me. If you Rick Moll me, I swear to God. Ooh, this is cool. This is 2-dimensional standing waves. Cool. All right. Bye, y'all. Thanks for the cool link, Logan. I will see you all at probably the review sessions. Have a lovely last couple days of classes. I'll miss you all.